In this video, we're going to talk about a topic called conditional probability, which we're going to try to introduce what this is using an example. So let's consider the table that's given in this problem. It's made up data, okay, but suppose it has data on patients who were admitted to a hospital on a given day. Okay, so how we read the table, the rows are telling you whether or not the patient had a heart condition. Okay, so yes or no. So if you're in the top row, it means that you did have a heart condition. And if you're in the bottom row, it means you did not. And then the columns are talking about what your blood pressure was. So was it high, was it normal, or was it low? Okay, so those are the categories. So if you want people, so someone walks in the hospital, you want to know how many people were there that did not have a heart condition, but did have high blood pressure. You would go no heart condition, so we're in this row. High blood pressure, so we're in this column, so it's going to be 20. Okay, so that's how we read from this table. Now let's try and answer some questions from it. Suppose we randomly select a person who was admitted to the hospital that day. We want to know the probability that they had high blood pressure and a heart condition. Okay, so I'm going to define some notation here. So let's let H be the person, the event, let's say, that the person had a heart condition. Oops. Okay, and I'm going to call B, and we're actually really going to care if they had high blood pressure. So B is going to be the event the person at the hospital had high blood pressure. Okay, so those are the notation we're going to use. So we want to know here, so we pick one person at random. We want to know what's the probability that they had both high blood pressure and a heart condition. So what we're looking for is the probability of H intersect B. So they were in the event that they had a heart condition, and they were in the event that they had high blood pressure. So what's our sample space here? So our experiment is to pick one person from this pool. So we're going to take one person and we do it randomly. We randomly select them. This randomness means that every person is individual or equally likely to be selected. So we have a uniform sample space. Okay, it's just the people that went to the hospital that day. So that means that in order to compute this probability, it's the number of people who had a heart condition and high blood pressure divided by the number in the sample space. Okay, so how many people were in the sample space? Well, we need to add up how many people were in this chart. Okay, so if we do it by row, the first row is 50 and the second row is 125. Okay, so that means that the total is 175. Okay, so there's 175 people who went to the hospital that day. So that's the size of our sample space. And the number of people who had a heart condition and high blood pressure is this spot here. So this probability is going to be 15 over 175, which if you compute into a decimal is 0.086. Okay, so that's a normal probability. Now we're going to talk about parts B and C that are going to seem pretty similar. So for part B, what's the probability that a randomly selected person who was admitted to the hospital that day with a heart condition also has high blood pressure? So we're still looking for people who have a heart condition and high blood pressure. Okay, it seems very similar. Okay, the most important bit is that they were admitted with a heart condition. Okay, so imagine that you go to the hospital, the first thing they ask you is whether or not you have a heart condition. If you say yes, you go to one wing, and if you say no, you go to a different wing of the hospital. What we're doing here is we're picking from the wing that has all the people with the heart conditions. So we know we're going to get someone with a heart condition, and then we want to know what's the probability that they also have high blood pressure. Okay, this is the idea behind conditional probability. So we know something about who we're going to pick from, or the group that we're going to pick. So the way I'm going to write this is probability of B if we know H. Okay, there's going to be better notation that we're going to talk about, but so because we know that we're picking people with a heart condition, let's restrict, the sample space is going to be that, okay? We're going to have a new sample space. It's people with a heart condition. So that's where we're picking. So that's what our sample space is going to be. And it's going to be uniform because we're doing it randomly. So every person in that set is equally likely. Now on the top, I don't want to write N of B because sometimes you're going to have high blood pressure with no heart condition, and we're definitely not going to get those people. So what we have on the numerator is actually B and H. Okay, so we already know they're in H, and we want to know the probability they're also in B. Okay, so that means that we're going to have 15, the same top, and now the number of people with a heart condition was 50. Okay, so this is 0.3 if you compute it. Okay, so let's just write a note. So we're definitely pick someone with a heart condition. So this is why we restrict the sample space. Okay, so this is what conditional probability does. It restricts your sample space to what you know is going to happen. So notice that it's much more likely now to get someone with high blood pressure if you know that they have a heart condition already. Okay, so the chances went up. Okay, what about the other way? Okay, so here we want the probability a randomly selected person who was admitted to the hospital that day with high blood pressure. Okay, so now we know that they have high blood pressure, also has a heart condition. Okay, so it's similar. So we want the probability now of H if we know B. So we know they have a high blood pressure. The top again is going to be the same, but now we restrict the bottom to people with high blood pressure. Okay, so you still have 15 people that have both. The people with high blood pressure is going to be this column. So 15 plus 20, so 35 in that column. So now we're going to divide this by 35, okay, and we get 0.43, I think. So this is even the most likely. Okay, so this is the idea behind conditional probability. If you know something about what could happen in the experiment, what's going to happen. So here we knew we were going to get someone with a heart condition. Here we knew we were going to get someone with high blood pressure. It affects the probability that other stuff can happen, or it can affect, I should say. Okay, so understanding the differences in the wording here is very important because this is conditional probability. Okay, so now let's define the notation, and then I'm going to come back here and rewrite these using the proper notation. So a conditional probability is a probability in which you already know some of the information. So there's something that you already know is going to happen or maybe is not going to happen, okay, about the outcome of the experiment. The notation we use looks like this. So it's PR, same as before, but now it's E with a vertical line and then F. Okay, so the way that you read that, so the vertical line, maybe I'll do that in red. Okay, the vertical line, normally you read as given that, or given, or such that. So let me just write what this equals. Okay, so this is the probability event E occurs given that event F has occurred already, okay, or definitely will occur. Okay, maybe you have some insider information. So in here, the first thing that you write is the one that you want. Okay, the second thing, so after the line, this is the one that you know happens. Okay, so that's the order. So I want to draw a little Venn diagram here. Okay, so we have our events. So there's our sample space. And then we have events E and event F. Okay, now what this says is that we know event F is going to happen. Okay, so that means when I pick, when I do the experiment, I have to pick among things that are in this blue circle. Okay, so everything else is kind of off limits. Okay, so we're definitely not picking anything here, and we're definitely not picking anything out here. So we know those are gone. And then what this is asking is, what is the probability that we actually pick something in here? Okay, so in the intersection, so you want to know what's the probability you get something in E if you know you're going to get something in F. Okay, so because F only has 2 spots, it means that you're in this blue, maybe I should have done it red. Okay, so you're in this red spot, so that's in E and F, and you're not in the other blue spot. Okay, so now when we're going to compute the probability, okay, so the probability of E given F, what we want to do is compute the probability of the intersection divided by the probability of F. Okay, your new sample space. Okay, so this is very important. If you're going to remember one formula, okay, this is it. Now, if your sample space is uniform, so all your outcomes are equally likely, the formula actually simplifies to the number of things, which is what we did in the previous example. So it simplifies to the number of things in the intersection divided by the number in F. Okay, so this, you have to be in a uniform sample space, whereas in this one, the first one that I did up here, okay, the sample space does not need to be uniform. Okay, so let me just write somewhere here. So this one does not require a uniform sample space. Okay, so that one works all the time. Okay, this one does require uniform. Okay, so you have to have a uniform sample space in order to use the counting, the number thing. Let's go back and just rewrite these. Okay, so the first one we already know. Okay, now instead of B, if we know H, I kind of tried to write it in the right order. What this one is, we want to know the probability that B happens given that H is definitely happening. Okay, so remember the one that we know, goes second because the line means given that, so or such that. So this don't already happen, and the one that we want is in the front. Okay, so similarly for part C, it's going to be the other way around. So this one is going to be the probability of H given that B is definitely going to happen. Okay, so you always want the one you want first. The one that you know is after the vertical line. So let's try an example. Suppose that the employees of a nearby grocery store are surveyed. Now here they're giving us probabilities as percentages. Okay, so it was found that 65% of the employees work full-time. Okay, 80% attend university, and 15% work full-time and attend university. So we're going to randomly select an employee. So what is the probability that a randomly selected employee works full-time given that they are currently attending university? Okay, so we're only going to talk to the ones that are attending university. Okay, so let's just write down what they give us. So full-time I'm going to call F. Okay, so F is works full-time. Okay, I don't want to use U, so maybe I'll use C for college. Okay, they attend university or post-secondary. Okay, so what did they give us? So 65% work full-time. So that's the probability of F is going to be 0.65. Okay, so if we randomly select a person from this grocery store, there's going to be a 65% chance that we get someone who works full-time. So the probability is 0.65. Okay, the probability that they attend university, so the probability of C is 80%, so 0.8. And the probability that they do both, so they're in F and C, is 15%, so 0.15. Okay, so that's what they gave us. And what they want is, so the probability a randomly selected employee works full-time given that they're attending university. So we want to know the probability that F happens given that we know C happens. Okay, so that's what we're looking for. Now, when you're trying to decide if it's conditional or not, look for these type of words. Okay, so given that, or if you know, okay, or you're picking from this group, so that can help you sort of tell whether or not it's conditional. Okay, so then if we try to compute this, we're going to use the formula. So it's the probability of the intersection over the probability of the one that we know happens. Okay, so the one that we know is the one that goes on the bottom. Know happens. Okay, now we have both of these numbers. So the intersection was 0.15, and the probability they attend college is 0.8. Okay, so if we compute this, it's 0.1875. Okay, but we didn't need to know the number of things because we already had the probabilities. Okay, let's try another one. So suppose students in a math class were surveyed on their TV watching practices. Okay, I'm going to try and write the information down right away. So 20% of the class watch more than 4 hours of TV. So T is going to be watch. Okay, more than 4 hours. So we know that 20% do that. So the probability of T is 0.2. Okay. So here, this is an interesting statement. Of those students. Okay, so that we need to be careful of. So it says, of those students, 75% watch Riverdale. I don't know if that's still on anymore, but so you have to, so the 75% is coming from the students that watch more than 4 hours of TV. Okay, so that means that you're in the T category. So actually they've given us, I should have done R. Okay, so R is watch Riverdale. They've given us a conditional probability. So they've given us the probability of R given T is 0.75. Okay, so that's what they've given us. What do they want us to find? Suppose one student in the math class is selected at random. Okay, so someone in the entire class is selected. What's the probability that they watch more than 4 hours of TV and Riverdale? So that's an intersection. So what we're looking for is the probability of T intersect R. Okay, now we can find this by again using the conditional formula. Oops. So I'm going to use the one that they gave us. So probability of R given T is going to be the probability of R intersect T over the probability of T. Okay, now notice that we have this and we have this, okay, and we want that. So we can rearrange this equation. Okay, so the probability of R and T is going to be the probability of R given T times the probability of T. So I just multiplied on both sides of this equation by the probability of T. And now I can plug in the numbers. So R given T is 0.75. Probability of T is 0.2. So we get 0.15. So there's a 15% chance that if you randomly select one student from this class, that they watch more than 4 hours of TV and Riverdale each week. Now, rearranging, so this, what we did was rearrange the formula for conditional. Okay, you can always do this. So if you want the probability of an intersection, what you can do is take the probability of one of the events and then times by the conditional probability where the one, so I'm going to use a highlighter here. So the one that you take is the one that you know happens. Okay, so I could do this in two different ways. Okay, so I start with E, or maybe I start with F. Okay, I'm going to get the exact same number. Okay, so notice that it always matches the one that I know happens. We can also generalize this to more events. Okay, so again, you pick, I'm only going to write this for one, but it works if you switch the E1, E2, and E3. So let's say we take E1, okay, so we take that one is going to happen, and then I'm going to do E2 next, so it's E2 given that E1 has already happened, and then I need E3 to happen, but I already know that E1 and E2 happened. Okay, so they just keep, you just keep increasing what you know has happened from the things that you did before. Okay, so you're welcome to use those. Let's just do one more example. So this one is a little bit trickier. Okay, so we have a box with 5 yellow marbles, 7 purple marbles. Okay, so that's 12 marbles total. If we select 5 marbles at random, okay, what's the probability we select at most 2 yellow marbles? If we know, okay, so here, this is our hint. If we know, we select at least 1 yellow marble. Okay, so when you see that if we know, given that of this category, okay, all of these things are telling you conditional. Okay, so I'm looking for a conditional probability. So I'm going to try to write some notation here. Okay, so let's say, so I want to know what's the one I want. We want the probability we select at most 2, so less than or equal to 2 yellow marbles. Given that, and then I know that I select at least 1 yellow marble. I missed the 1. Okay, so this is the one that I want. Okay, this is the one that I know is going to happen. So I use the formula because it's hard to work with the conditional. So I'm going to switch. So it's the probability that I get at most 2 yellow and at least 1 yellow divided by the one that I know, which is the probability I get at least 1 yellow. Okay, so I want to compute these. Now, sometimes people have trouble with these weird intersections. Okay, so let's think about this one. How many yellows could I get? I'm going to try and do a number line over here. So the fewest I can get is 0. I have 5 yellow and I'm picking 5. So the most I can get is 5. Okay, and then I have 1, 2, 3, 4, 5. Okay. So if I get at least 1 yellow, oh, maybe I don't want to, shoot. Okay, let's not do that. I'm going to do it on the top because I'm talking about the intersection. So if I get at least one yellow, it means that I got one yellow or more. Okay, so I have to be in this part of the number line. Okay, if I get at most 2 yellows, it means that I got 0 up to 2 yellows. Okay, if I want the intersection of that, I want to look for where they both happen. Okay, so it's 1 and 2. So I could rewrite this, the probability that the number of yellows, maybe I'll do a number sign. Okay, so the number of yellow is between 1 and 2. Now, for the bottom, we want at least one yellow. Okay, look at that green bit. Okay, it's 1, 2, 3, 4, 5. That's a lot of cases to do. So we might want to think about the complement, which is 1 minus the opposite. The opposite is 0 yellows. Okay, so just one case. So now we want to try and compute this. Okay, the top still doesn't look very nice, so it might be better to split into cases. Okay, 1 yellow plus the probability of 2 yellow over 1 minus the probability of 0 yellow. Okay, so now we want to try and figure out what these probabilities are. So I'm going to compute the probabilities, each of them. Okay, so I'm going to have a bigger fraction here. So what's the sample space? And is it uniform, I guess? Okay, so we're selecting 5 marbles at random from 12 marbles. Okay, so we're going to do 12 choose 5. Okay, that's how many things are going to be. So we're assuming that all of the marbles are different because there's 12 distinct marbles. Okay, so we're assuming that we can tell them apart. That's going to give us a uniform sample size. Okay, so all of these denominators for these probabilities are 12 choose 5. Now, okay, so for 0 yellows, so that's on the bottom, okay, that means that all 5 of our marbles come from this purple set. Okay, so that's going to be 7 choose 5. Okay, so all 5 marbles came from purple. If you want to include the 5 choose 0, okay, you're welcome to do that there. If we get 1 yellow, it means that from the 5 yellows we picked 1, and then from the 7 purples we picked 4. Okay, so I'm going to do 5 choose 1 times 7 choose 4. If we want exactly 2 yellows, same idea. Okay, pick 2 of the yellows and then pick 3 of the purples. Okay, and then we can just compute all of these. So I think it's 0.221 plus 0.4419 over 1 minus 0.0265. Okay, and you should get, if you compute that, 0.681 as our answer. Now, one thing I do want to say, so we could have done this another way. Because we had a uniform sample space, okay, instead of the probability, I could have done the number. Okay, the number of 1 yellow plus the number of 2 yellows over, now you need to be careful. Okay, so here's where people often make mistakes. So instead of 1 minus the number, I have to do the sample space. Okay, the number in S. So if I was to rewrite this, so essentially from here, I could multiply the top and the bottom by 12 choose 5. Okay, that would kill off all those denominators, but it would make this thing equal to 12 choose 5. Okay, it will get you the same answer. So you could have 5 choose 1, 7 choose 4, plus 5 choose 2, 7 choose 3. All that would be over 12 choose 3 minus 7 choose 3. Sorry, 5. I don't know where 3 came from. Okay, and that's going to give you the exact same 0.681. Okay, so you want to be careful. I just wanted to illustrate the difference here. So if you're using counting, when you're doing the complement, you have to use the sample